Good afternoon. Thank you for joining this presentation. My name is Paul Balcázar, and I will talk about an assessment of two equation RANS turbulence models when applied to high Prandtl number forced convection in a pipe. The content of this presentation will be an introduction of high Prandtl number fluids and their applications, the objectives, methodology, results, and a summary of conclusions and recommendations. The introduction. The Prandtl number is a ratio of the dynamic viscosity, which represents momentum diffusivity, and the thermal diffusivity of a fluid. This means that this parameter indicates what mode of heat transfer is dominant, whether it is convection or conduction. Additionally, it can indicate the relative sizes of the thermal boundary layer and the velocity boundary layer, with Prandtl equal to 1 being the case where both boundary layers are the same thickness. This leads to two limiting cases, the first of Prandtl tending towards 0, where the thermal boundary layer is much thicker than the velocity boundary layer, and this behavior is observed in liquid metals. On the other hand, there are Prandtl numbers tending towards infinity, which are the ones that are relevant for this investigation, where the thermal boundary layer is much thinner than the velocity boundary layer. In fact, the region of conduction develops completely within the viscous sublayer, where the flow is laminar. High Prandtl number fluids have been widely used, for instance, in the automotive industry with engine oils and coolants. However, other high Prandtl number fluids have gained relevance. For instance, molten salts are used in solar farms as working fluid to remove the heat, as well as for thermal storage. Additionally, there are molten salt nuclear reactors designs that are becoming popular. In terms of computational fluid dynamics and methods for solving turbulent flows, we have direct numerical simulation, or DNS, which solves all turbulent structures directly, from the largest eddies to the smallest ones known as the Kolmogorov scales. This requires that the grid be smaller than the Kolmogorov scales in order to fully resolve them. This leads to a high computational cost associated with this method, and it limits the flow conditions and geometries that can be applied. On the other hand, we have large eddy simulation, or LES, which applies spatial filters to differentiate between the largest structures, which will be directly resolved, and the smallest eddies, which will be modeled. On the other hand, we have Reynolds average Navier-Stokes equations, which are time averaged, meaning that they ignore the instantaneous fluctuations of turbulent flow, and they focus on the mean behavior of the system. They add Reynolds stresses to the equations, which means that now there is a closure problem where there are more variables than there are equations and the system cannot be solved. So what RANS models do is they add equations to the system to close it. Although these are very popular methods, their applicability to high Prandtl number flows is still limited, and it requires further studies to determine how they will perform. This leads to the objective of this investigation, which is to evaluate the performance of RANS turbulence models for high Prandtl number pipe convection. Specifically, two turbulence models are used, the K-epsilon model with enhanced wall treatment and the K-omega shear stress transport, or SST. The flow conditions are the following, with three Prandtl numbers, 6.7, 18.7, and 24, and a range of Reynolds number from 7,000 to 85,000. In terms of the methodology, the first turbulence model, the K-epsilon, is the most popular one in industry because of its simplicity. The two equations that adds is turbulence kinetic energy K and the rate of energy dissipation epsilon. And it is designed to be used for high Reynolds number flows or away from walls, because in the near wall region, both of these parameters tend towards 0. For this reason, wall functions are applied in order to model the flow between the wall and the first computational node. In this case, it was the enhanced wall treatment. The K-omega model is also very popular, and it replaces the second equation by the dissipation of kinetic energy into heat, or omega. And it is applicable near walls because in the near wall region, the kinetic energy of the Kolmogorov scales is transferred into heat because of the viscous forces in the fluid. It is preferable for viscous sublayer modeling, and it is in fact this characteristic that is useful for high Prandtl number fluids because inside the viscous sublayer we have the region of conduction. The geometry of the system is a pipe of circular cross-section based on the experiment by Everett and Carroll in 1945. It was solved axisymmetrically in ANSYS Fluent with a constant wall heat flux and a uniform inlet temperature and velocity. Additionally, all data for analysis was taken from this radial line at approximately 50 diameters from the inlet. And two verification checks were made. The first to ensure that all results were mesh independent, meaning further refinement in the grid would not have any effect on the numerical results. Additionally, there was a check on the thermal development of this location to ensure that it is outside of the thermal entry lane, meaning there is no further changes in the thermal field in the axial direction. Now, all K epsilon cases were mesh independent, and I will talk in future slides about what happened with the K omega cases. So the results. First of all, I will talk about this mesh sensitivity specifically for the K omega case. As the mesh is refined in terms of the placement of the near wall node, there are peaks and variations in the resultant Nusselt number. For this reason, these test cases were also investigated in terms of higher Reynolds numbers closer to the ones expected to be seen in industry. For example, 50,000 in blue and 100,000 in burgundy. And as can be seen, there are dramatic changes in the Nusselt number with grid refinement. And for this reason, this model for high Prandtl, high Reynolds applications loses some of its reliability, or most of its reliability. In terms of the Nusselt number predictions, we compare the numerical results of the K omega model in red squares and the K epsilon model in green X's with the experimental data presented by Everett and Carroll. In the case of Prandtl equal to 6.7, we see that there are great discrepancies between the numerical and the experimental results. In the figure on the right, we see that the K epsilon model in red, which is the most accurate in this case, has errors of approximately 20% and less. On the other hand, the K omega model has errors of 30% and less. In any case, both errors decrease with an increase in Reynolds number. And it is this characteristic or trend that we will see in the other Prandtl numbers that were studied. In the case of Prandtl equal to 18.7, we see that both turbulence models do a much better job in estimating the thermal behavior of the flow. K epsilon in red has errors lower than 4%, and the K omega still does a very good job with errors lower than 10%, which is very good for thermal predictions. Additionally, the error of both models still decreases as Reynolds number increases. It is worth pointing out that for this and the previous Prandtl number test cases, both turbulence models overestimate the Nusselt number. Additionally, the K epsilon remains the preferable one for these models. Conversely, when we look at Prandtl number equal to 24, we see that there is a shift, and now the Nusselt number is underestimated. And the K omega does an excellent job at predicting the Nusselt number from the experimental results. As can be seen in the figure on the right, there is a very large error in the K epsilon model for Reynolds of 7,000. And that is because at this number, there is still a transition between laminar flow and turbulent flow. The behavior that we saw in these Nusselt number predictions can be explained by looking at the mean temperature profiles of these flows. For instance, when we look at a Reynolds number of 7,000 in the blue and orange lines, there is a large discrepancy between the predictions of both turbulence models. However, when we look at a higher Reynolds number, such as 25,000, the difference between models is much smaller. And this is because both models work better at high Prandtl number applications. Additionally, it is worth noting that consistently, the K epsilon model in blue and in yellow provides higher magnitude of the logarithmic temperature region in both cases. And these trends are seen across all test cases. It is worth pointing out that compared with air, for example, that has a Prandtl number of 0.72, and it's very common both in experiments and numerical analysis, where the turbulence models and the Reynolds number have little to no effect on the resulting mean temperature profiles. One of the more interesting effects of the Prandtl number is the conduction sublayer thickness, and this is very relevant for this study. We look at this parameter, which is the turbulent viscosity over the turbulent Prandtl number divided by the molecular viscosity over the molecular Prandtl number. When this parameter is less than 1, it effectively defines a region where conduction is dominant, or a conduction sublayer. As can be seen in the figure on the left, as Prandtl number increases, this conduction sublayer becomes much, much thinner. And it is this Prandtl number effect that makes high Prandtl number fluids so difficult to model using CFD, because the mesh resolution in this region has to be very high in order to capture the thermal and velocity gradients. This can be translated into the mean temperature profile, as seen on the right. As the Prandtl number increases and the conduction sublayer becomes thinner, the magnitude of the logarithmic temperature region becomes greater. And the difference between this curve and what is expected from a Prandtl number of 1, shown in black, is much greater. Now, a summary of these results. First of all, there was no mesh-independent solution for the K omega cases. And this is because of that high sensitivity to the placement of the near wall cell. And this sensitivity increases with Prandtl number and with Reynolds number. For this reason, caution is suggested when there is an application of high Prandtl, high Reynolds flows, because this model will not reach a mesh-independent solution, and it is not possible to determine whether your model has been constructed and resolved correctly. On the other hand, we have Prandtl number equal to 18.7 and equal to 24, which showed good agreement between the numerical and the experimental results with errors lower than 15%. However, for Prandtl equal to 6.7, there were high errors. It's worth noting that for Prandtl number equal to 0.72, both models did an excellent job at predicting the thermal behavior, pointing towards an issue specific to Prandtl number equal to 6.7. As Reynolds number increased, there was better performance from both turbulence models, with a decreased error both relative to the experimental data and relative to each other. And this was explained by the mean temperature profiles. Finally, when we look back at the objective of this investigation, we see that RANS turbulence models can be applied to high Prandtl number convection with constant wall heat flux. Specifically, the K epsilon model with enhanced wall treatment is preferable for lower Prandtl number cases where modeling of the viscous sublayer is less relevant. Additionally, in these cases, the Nusselt number is underestimated. On the other hand, as Prandtl number increases and modeling the viscous sublayer is more important, the K omega SST becomes preferable. And it underestimates the Nusselt number from the experimental data. Overall, both models perform better at higher Reynolds numbers, and it is because both models also perform better when there are no viscous effects present. Finally, some recommendations. There should be a verification of the mesh resolution inside the boundary layers. All meshes were constructed such that the near wall cell is within y plus less than 1. However, it is important to also note that there have to be enough nodes within the boundary layer region to properly capture the gradients of all variables. Additionally, there should be further investigation of the K omega mesh sensitivity to determine its range of applicability and how this sensitivity can be reduced, whether it is by decreasing the y plus of the near wall cell or by increasing the number of nodes in the boundary layer. Finally, there should be a study of a variable turbulent Prandtl number in these flows. Recent studies have shown that as Prandtl number increases, the turbulent Prandtl number becomes more variable in the near wall region, and this variability can affect the results of thermal predictions and make RANS turbulence models more effective. Thank you very much, and please feel free to contact me for any questions or comments. I would be happy to talk to you about this. Thank you very much.